Okay, get started and continue where we left off last time with few recap questions. So why is it important to analyze proteins? We talked about a lot of different reasons. Let's kind of capture a couple. Yeah, Jean? Huh? For quality control. Yes, definitely. It's a good answer. What else? Yeah, nutrition labeling. So quality control, nutrition labeling. And we talked a lot about research. When we're doing research, we need to determine protein content in certain assays. So we can assess functionality based on protein content, for instance. We also, when we're isolating proteins and we need to characterize them, we need to know how much protein we have in our solution or our extract. Also, when we are producing an industry protein concentrate, protein isolate for different labeling or not labeling for different sheet specifications, is it a concentrate? Then it has to have over 60% protein or over 80% protein versus an isolate over 90 in some cases, over 80 in other cases, depending on the source of that protein. We talked about enzymes being proteins as well. So basically, an enzyme is a protein. Yes, biological activity there. So an enzyme is a protein. So in order to determine the activity of that enzyme, we need to determine how much of that enzyme mix that we have is protein. So we can determine activity per gram of protein over the amount we have on the bottle of the enzyme that we purchase. So other than that, that's basically most of the things we talked about in terms of reasons for analyzing protein. So in terms of conversion factor, a couple of the methods we're going to learn in the lab are determined based on nitrogen content, and we convert nitrogen content to protein content using a conversion factor. So why could it be different? Yes, different proteins have different nitrogen percentages because of different amino acid composition. Some amino acids are basic amino acids. They have extra amino groups in the R chain. So therefore they have, if you have higher basic amino acid in the protein, then you have higher nitrogen percentage, then the conversion factor will be lower. So, for example, we talked about last time, wheat protein has a conversion factor of 5.7. Cheese has a conversion factor of 6.38. Which one of those have more nitrogen percent would be the wheat. So the wheat will have higher nitrogen percentage, therefore it has lower conversion factor. That means the wheat protein has more basic amino acids than the cheese protein. So there is a table in the chapter, in the protein chapter in the textbook, that gives you a conversion factor for different sources of proteins. So you have one for rice, one for wheat, one for cheese, etc. So there are several others in that table. And these nitrogen conversion factors are calculated based on the amino acid composition of the proteins. Once we know the amino acid composition, we can derive their nitrogen factor. Now, when we don't know the nitrogen percentage of a particular protein, we tend to use the average one, which is a 6.25. So let's say in an exam, I don't give you what protein. I don't say dairy. I don't say wheat. Then I expect you to default to the 6.25 conversion factor. If I say cheese, you've done it in the lab, or next week you'll be doing it in the lab, and you're going to do calculation, you're going to remember it's 6.38. So if I say protein content in cheese, I would like you to use a 6.38 conversion because you will remember it. So you're going to do the calculation multiple times. So you remember that you use that conversion factor. Okay, so so that's that. What are the three reaction steps of Keldal? We started with Keldal. We talked about the different reactions, and we stopped at the calculations. So what are the three? Okay, here they are: digestion, distillation, and titration. Yes. So the three steps are digestion. We digest the protein. Let me go back to that slide because we want to go to calculation. So I want to make sure that you know what we're talking about. So we digest the food sample with concentrated sulfuric acid, and with the presence of heat and a catalyst. And we talked about the reason of a catalyst to increase the boiling point of sulfuric acid to have more efficient digestion and a fast digestion. So the sulfuric acid digests the food. Everything gets converted to gases, so fumes, CO2, H2O, SO2. But the amine groups in the protein, the amine groups that have the nitrogen, react with the sulfate, and it gives you ammonium sulfate. From there, we are going to follow the nitrogen because we're calculating nitrogen percentage. So the amine group with the ammonium sulfate, we will react it with NOH. So the NOH is a base, so part of it is going to neutralize the acid, and part of it is going to react with the ammonium sulfate to give you ammonia gas. So now your nitrogen is in the form of ammonia, and the ammonia will be captured by boric acid. So that happens during the distillation. So ammonia and water will evaporate, or will ammonia is a gas, obviously. It will leave the sample solution, and along with it, the water vapor, and they will get distilled into boric acid. The boric acid will react with ammonia in the presence of an indicator, which is methyl red indicator, is going to convert to ammonium borate. So it goes from red to yellow. That's the indicator changing color at different pH. So you will have ammonium borate. Then we titrate borate with acid, which is a standardized HCl. To bring back boric acid, the color changes from yellow to pink. The last drop of the titration is going to convert the color from yellow to pink, and that would be the end of titration. Now, what you want to remember, now we're going to do the calculations together. What you want to remember is number of moles at equilibrium are equal. So number of moles of borate at equilibrium will be equal the number of moles of HCl at equilibrium when we reach the end of the titration. And if you look at the equation above, you have 1 mole of ammonium reacting with 1 mole of borate. So 1 mole of borate is equivalent to 1 mole of ammonium, and in ammonium you have 1 nitrogen. So 1 mole of nitrogen is equal to 1 mole of HCl at equilibrium. So number of moles equal number of moles at equilibrium. That's what you want to remember now as we derive the equation down here to calculate percent nitrogen. So at equilibrium, at the end of the titration, that's what you want to remember. Number of moles of nitrogen equal number of moles of HCl. All right, so I'm going to write this down here behind me and start deriving the equation with you, the equation that you see. Once you understand how we derive it, you will remember it because you need to remember this calculation Because in an exam or a quiz, you might be asked to calculate percent protein when I give you some given numbers. So in order to remember this equation, now you're going to look at it like, oh boy, how I'm going to remember all these numbers. You will remember it if you simplify it, and that's what we're going to do now. So I'm going to say number of moles of nitrogen equal number of moles of HCl at equilibrium. Okay, so that's what you want to remember. And what else do we want to remember? Number of moles equals mass over molecular weight. This is always something you want to remember. So number of moles equal mass over molecular weight. That's chemistry, general chemistry. Remember that. Okay. And what else you want to remember? You want to remember that number of moles or number of equivalents or number of moles equals molarity times volume or normality times volume. So you would remember that, and you need to remember that. Okay, if you remember that, then it's going to be easy to understand how I'm going to derive this equation for you. So I want to get percent nitrogen. Okay, that's my target. I'm calculating percent nitrogen in my sample, and I want to convert it to percent protein using the conversion factor. Now, to get to the percent nitrogen, I will have the weight of my sample, obviously, because at the beginning, you're going to weigh out an amount of sample, so you know the weight of the sample. And you need to know in grams your nitrogen so that you can divide grams of nitrogen by grams of sample times 100, so you can get grams per 100 grams. So percent nitrogen is basically what you're looking for is grams per 100 grams of sample. So now what I want is the mass of my nitrogen. Okay, so I need to solve for mass. I need the amount of nitrogen. So in order to solve for mass, here's the mass. So I'm after this. My unknown is mass in this equation. So if I put mass equals, oh, sorry, let me write that out. Mass equals, let me go to that slide so you see where I'm deriving things. Mass equals number of moles times molecular weight. Perfect. So now I have mass of nitrogen. I'm solving for nitrogen. I need the molecular weight of nitrogen. And the number of moles, where do I get that? I get that because I have molarity times volume. I'm titrating. So I have the volume of my HCl and I have the normality of my HCl. And I already told you number of moles of nitrogen equal number of moles of HCl. So if I want to get number of moles of HCl, I can do so because I'm going to tell you that the normality is 0.1. That's what I'm going to use for HCl, the 0.1 normal standard HCl. That's what I'm going to use for titration. And when you titrate and reach the end point, you're going to read the volume from your burette. So that information you're going to have. So basically, here, I'm going to replace this end here. I'm going to say the mass of my nitrogen equals number of moles, molarity or normality, it doesn't matter, times volume, but the volume is in liter, because normality equals number of moles equals molarity. Molarity is number of moles per liter, and volume is in liter. So that's the unit. So in liter times my molecular weight of nitrogen. I have the normality of HCl. I will titrate. This value is going to be in milliliter. When I titrate, it's going to be in milliliter. I need to convert to liter. so that I have the correct units. So basically, my normality times volume, if I want it in milliliter, is going to be divided by 1,000. So I'm converting. I'm converting my liter into milliliters. So I divide by 1,000. Okay, and then times the molecular weight of nitrogen. Are we all following? If you have any question, I can stop and repeat. I can repeat anything if you have any questions at this point. Otherwise, if you're following, we're getting close here. You have the mass, we get the normality of HCl, we'll get the volume of HCl from the burette, and it will be in milliliters, so I need to convert that to the correct unit. I divide by 1,000, and I need the molecular weight of nitrogen, which I already know, because either I will give it to you in the question, or you would know it in the equation. It's 14 grams per mole. So that is the molecular weight of nitrogen. Now the normality of HCl, I'm going to tell you it's 0.1 moles per liter. Okay. And you get the volume from the titration. And if I want percent nitrogen, in this case, I will put the weight of sample down here. So the mass divided by the mass of nitrogen divided by the weight of sample. And all of this times 100 to get a percentage. And there is your equation. And that's what it is right here. That's what we just derived. Okay, now what does it mean corrected acid volume? We will be running a blank. And why we will be running a blank to correct for any nitrogen that might come from any reagent we've used in the Caldala assay. So you have to correct for any nitrogen contamination, anything in the reagents. So we will be doing a digestion for a blank sample, putting an empty wax paper in the digestion tube, putting all of the reagents, running it through the entire assay, and then we titrate it. The volume might be very small, it might be 0.1 milliliter, 2.5 milliliters, depending on any contamination of nitrogen. So to correct for that, so we take the volume that we needed to titrate the sample minus the volume we needed to titrate the blank. And then we correct for that, and that's the value you use. Any questions on that? Okay. All right, so let's practice. So that's for a +2. Again, we'll have Laura Brigida put up extra credit on Canvas for what's today's date? Wednesday, for Friday by 5 p.m. for the protein calculation. So go ahead. So how are we doing? Any answer so far? Are we stuck anywhere? If I give you the percentage of nitrogen, you just take 100 divided by 17.5 to get the conversion factor. You got an answer? To dry bases? Okay, so what did you get on wet bases? 19.9? Yeah, 19.9, and the other one was 19.62 or 0.6. Yeah. So on what basis? Let's look at this together, okay? Since we have at least one person that solved it. Okay. So that's your equation that we just derived together. The given, it's simple. We have the given, the normality of HCl, and we have the volume in milliliters, and then the all the units will cancel because normality, number of moles per mil, and molecular weight, which is 14 grams per mole. So all of the units will cancel and we'll get grams per 100 grams. All right, so what will happen here, you replace normality by 0.1142, and then the corrected volume is for one rep, the first rep, 22 milliliters minus 0.2, which is the blank. So sample minus blank. You have the weight of the sample. The 1,000 down here is also to correct from milliliters to liters to convert. And the 14 grams per mole, which is the molecular weight. You just do the calculation and you get the amount of nitrogen. The 3.43 is percent nitrogen. Then you convert to protein by multiplying by the conversion factor. So I gave you, in this case, I gave you a percentage of nitrogen in the pentopene protein. I can give you a percentage of nitrogen. If I give you a percentage, 100 over the percentage would give you the conversion factor. Otherwise, I would give you the conversion factor. And you just multiply the percent nitrogen by the conversion factor, you get the percent protein. You do that for rep 1, you do it for rep 2. So you don't average anything until you get the final two answers for rep 1 and rep 2. Then you get your average protein content by adding okay, so there should be a division by 2 here, which I don't have. So you add the 2 and you divide by 2 because you have 2 replication, you get 19.7. And you want to convert wet bases to dry bases. We solved that when we were covering the moisture content. So we said we have 8% moisture. That was one of the givens. So 8% moisture, that means you have 8 grams of moisture in 100 grams of sample. So how much solids do you have? 100 minus 8 is 92 grams of solid. So of this solid, you have 19.7 grams protein of the solid material of 92 grams solids. How much percentage on dry bases? That means how much do I have in 100 grams of solids. So you would say 19.7 grams times 100 grams over the 92 grams of solid material, then you get 18.1. Oh, or the other way around. Is this, what did I give? A dehydrated, okay, I missed that. So, okay, forget about everything I wrote up there because I'm converting now from dry bases to wet bases. Because the value that I've gotten here is apparently on dry bases because I said dehydrated pre-cooked pinto bean. So here, these values, this value is on a dry basis. So 19.7 is on a dry basis. So again, here, the 19.7 is actually in 100 grams dry matter, okay? So the 19.7 grams protein is in 100 grams dry matter. Sorry, I confused you there earlier. How much would I have in 92 grams of solid matter? Because if I take away the moisture here, I get 92 grams of solids. So how much proteins I have out of 92 grams of solid in 100 grams of sample that has 8 grams of moisture? Then it would be 92 grams times 19.7 over 100 grams. That gives you the 18.1 gram or percent. Grams per 100 grams or percent. Okay. Holland asking what's 18.1% for? So this is percent protein on wet basis. So we started with a dehydrated sample. If we want to determine the protein before we dehydrate it, so as is, when we say wet basis, that means what it means is as is, before we did anything to it, before we dehydrate it. So that's why we take into account the percentage of moisture here and determine the amount of the percent of the protein in a sample that was original before we dehydrated. That means in an original sample, you have in a percentage, if you have 100 grams of original sample, 8 grams of this original sample is moisture, 92 grams of this original sample is solid. And protein belongs to the solid, is not belongs to the solid, is part of the solid matter. Everything is part of the solid matter. Your ash, your protein, your fat, your carbohydrate, they all sum up the dry matter. Everything is dry and only the moisture is moisture. That's why we take the moisture out and we get the 92 grams here. And that's why we take into account the moisture content. When you remove it, you have 92 grams. And if you have 19.7 grams in 100 grams dry matter, we need to know how much of that protein would be in 92 grams dry matter. And that's what the 18.1 is. Okay. I hope that answered the question. Moving on. All right, so the next method that you will be doing in the lab is the DOMAS, which is another official method of analysis to determine protein content, and it's also based on measuring nitrogen. So we measure nitrogen, total nitrogen again here, and we convert to protein. And the DOMAS is based on, is a nitrogen combustion method. So what does that mean, nitrogen combustion? It's based on combusting the sample at really high temperature. So we have an equipment made by a company called LECO. The method is DUMAS. The LECO is the equipment or the company that makes the nitrogen analyzer. So the equipment is nitrogen analyzer. DUMAS is the method that states the principle of the nitrogen analysis. Okay, so we have a nitrogen analyzer made by a company called LECO. There are different types of nitrogen analyzers out there. This is the one you'll see in the lab. We have a newer one in a research lab that we potentially will run your samples on the newer one. But the one that you'll have in the lab and you'll see it is the one that we have picture of up here. So what you see here is we have a carousel. Let me see if I can go there with my cursor. Where is it? Oh, there it is. So see this carousel here? And in there you would put little containers. We call them, what do we call them, Al? What? Capsules. Yes, I always forget that name. So little capsules that you would weigh your samples in, and you would put, we weigh about 0.1 grams of sample, and we put it in little capsules, and we put these capsules inside of these different compartments in the carousel. And uh, in a timed fashion, the carousel turns and each capsule gets dropped. It gets dropped into the combustion chamber right here. And the combustion happens at really high temperature, about 950 degrees. So everything, it gets the combustion happen with the presence of oxygen. So everything gets combusted, and you get everything converted to NO2, CO2, SO2 if you have SO2, H2O. So all of these, your sample is going to convert into oxides, I would say. So then if the gases now are going to move into a compartment where it cool it down and captures some moisture potentially. So the gases get cooled down, and they get directed into a ballast. So there is a ballast here in the back where all of your gases are contained here, and it's flushed with oxygen. So after that, after they go to the ballast, and they go from the ballast back to the front to a compartment where where there is copper, and the copper reduces your oxides. So it converts NO2 to NO2, NO3, NO, anything, or you have all the oxides you have into nitrogen. So NO2, NO3, NO, they would convert to N2, so nitrogen gas. So that converts it to nitrogen gas, and what's remaining is mostly your CO2 and H2O. They get to go to scrubbers. So we have scrubbers here, one for CO2 and one for moisture. So the CO2 and the moisture gets scrubbed off, and what gets carried with the helium is our inert gas. So what gets carried is nitrogen. Only the nitrogen get carried into the detector. And the detector in this case is thermal conductivity detector. So similar to the detector you learned in the GC lecture. So the nitrogen gas will change the conductivity as it comes, because you have helium and then you get nitrogen in there, and you get a change in conductivity, and therefore you were able to determine nitrogen content. Obviously you need calibration. We calibrate it with standards, and we get nitrogen percentage that way. It's very quick. It's, it's 4 minutes on average, or sometimes less. that you'll get the reading. So it's very quick, highly instrument based. You don't do anything other than you weigh in your sample. But that's theoretically, you don't do anything. You have to make sure that the equipment is running well. It requires a lot of maintenance, a lot of care. You have the appropriate gases there. You don't have any issues. And you also need to be calibrated and ensure calibration each time before you run it. You run blanks, you run standard, you just make sure that it's running properly before you start running your samples. But once the equipment's up and running and there's no issues and it's calibrated and ready, you can run a lot of samples in a very short, relatively short period of time. Compared to CalDAL, it takes much more of your time in terms of during the analysis. It has a lot of chemicals, takes a lot of time, long time to digest. You can process few samples at a time. Whereas here, you can process multiple samples in a shorter period of time. This is kind of a schematic of a nitrogen analyzer. In this case, it's just kind of a drawing of what you would have in terms of compartments, but it's your gases for combustion, and you have the carousel. Let's see where my pointer is. Carousel, the combustion, the cooler goes to a scrubber, and mixing of the gases, and reduction of NOs to N2. And sometimes you have a column here that would separate the different gases. Sometimes you don't. In the equipment we don't have a column that separates. We have scrubbers that scrubs off CO2 and H2O and only sends N2 to the detector. Okay. You will be running, well, at least seeing the RICO or the nitrogen analyzer in lab next week. So the common question is comparing methods, right? So you have the CalDAL and you have the DUMAS. You're going to run both of them on your sample. In terms of principle, you're going to you need to be able to differentiate the principle of each. So that's a common question that I would ask. What's the principle of CalDAL versus principle of DUMAS? Both analyze nitrogen, right? We're both determining nitrogen content. However, one is based on chemical analyses and one is based on combustion. So the chemical analysis, you have to know that you have three main chemical reactions: digestion, distillation, and titration. And you have to know that what happens to the nitrogen in each step. So you really need to know the chemical equations. You need to know where the nitrogen goes at each step. The DUMAS, all you need to know really is the food sample combusts, all the gases move into the system, and all the gases get scrubbed. The nitrogen oxides get reduced into nitrogen gas, and it gets detected by thermal conductivity detector. So instrumentation, it's highly instrument-based, the DUMAS is, whereas the CalDAL is mostly, a lot of it is operator-based and a lot of chemical reaction. You use a titrator, there is an automated titrator, but you're going to be the ones titrating. There's the distiller and there's the digestion block, but it's not highly instrument-based as the DUMAS is. Cost is much cheaper to run CalDAL versus running the DUMAS method. The reason it is cheaper, first of all, the equipment that you need to run CalDAL is cheaper. Digestion block, distillation unit, and then titration. Not very cheap, but much cheaper than the LICO or the nitrogen analyzer. It's thousands of dollars, and it's high maintenance, and it's very moody, get cranky a lot of times, and we just have to maintain it. So it takes time to maintain. It's expensive equipment, but it's definitely more throughput. That means you can analyze more samples in less amount of time. There's no chemical agents involved, so potentially safer. And in terms of application, both are official methods of analysis. Both are based on nitrogen determination. So accuracy and precision is very, very similar. Okay, other methods of analysis that are not official methods of analysis, we have the infrared methods of analysis, very common, fast methods, quality control. During processing, that would be the best option you have rather than running Keldol or having an expensive instrument to run all the time. So IR is commonly used for quick analysis of protein. You can use mid-IR to determine and the number of protein based on the vibration of the amide group. And you use infrared near IR based on the vibration of the NH bond. So they are fast, like I said, and takes less than 2 minutes, 30 seconds to 2 minutes. It does require calibration. So we need standards, we need to calibrate. That means we have to run all of these standards by either Kelda or Dumas in order to calibrate the NIR and run our samples. There are research methods, and we rely on them a lot when we're doing protein research. Especially if we have a solution with protein in it and we want to run a certain activity assay, we need to determine how much protein we have in this solution before running our next assay. So we tend to use quick research methods. Research methods that I'm going to give you examples on rely on measuring absorption. So your solution needs to be clear. So oftentimes when we prepare our sample prior to adding our reagent, we prepare the sample, we centrifuge, we take the supernatant, and we use that supernatant to react with our reagents in the assay and determine absorbance. Now, the problem with that, if you have a solution where it's turbid, that's why we centrifuge, it will interfere. Turbidity is going to interfere with the absorbance. It's scattering light, it's going to give you false high absorption. Also, another problem, if you have a protein solution and when you centrifuge, half of your protein precipitate, then you are underestimating your protein content. So that's another issue with these assays. So we have to be very careful in relying on them for accurate quantification. They're good for comparison. They're good when you have clear soluble protein solutions. Um, so the bisynchronic acid method, or in short BCA, we use it a lot in our lab. It's very simple. It basically relies on the reduction of cupric ions to cuprous by the proteins. So the peptides can reduce cupric to cuprous. Also specifically components of amino acids, cysteine, tryptophan, and tyrosine are highly reducing. They have highly reducing power, so they can reduce cupric ion to cuprous. And the cuprous ion that are reduced in the presence of protein react with BCA reagent and gives you a distinctive purple color that we measure absorbance at 562 nanometer. So because it's an absorption method and absorption is dependent on concentration, we have to have a calibration curve. So we have to plot uh, standard concentrations and measure absorption, have a standard curve, then we can determine the protein content in our solution. Oftentimes, we use BSA, which is bovine serum albumin, as a standard protein. So bovine serum albumin, we purchase that as a standard, we prepare different concentration, and we measure absorption at different concentration, and we plot our standard curve. Okay, another method, just last minute here, another method is the Bradford dye binding method. That's what you're going to do in the lab, but not necessarily on your samples. You're going to analyze a whey protein mix or concentrate. So this is an assay based on the protein reacting with a dye. In this case, it's Comasi blue dye, which upon reacting with the protein, it shifts from red to blue, and you measure at 595 nanometer. The interaction of Comasi blue with the protein depends on the amphoteric nature of proteins. Now, what amphoteric means is the proteins have basic and acidic components. So it relies on this characteristics and also on the hydrophobic interaction of the dye with the protein. So, and then you also need a standard curve, and we also need bovine serum albumin as a standard. You're going to prepare a standard curve using different concentration and preparing your sample and measuring the sample absorption and relate that to use the equation of the line to calculate concentration. It is sensitive and rapid. Not necessarily, there might be interference with certain reagents and small peptides might not be as reactive. You might not have the right residues or functional groups to react with the Comasi blue assay. And it's really good for low concentration solutions. And again, need to be clear, not turbid, in order to get good readings. So these assays, the research methods assay, usually we do not use them to quantitate in food samples. They give you good approximation, good comparison, but not necessarily official methods or even quality control methods that we use to determine protein content. Okay, with that, I'll end here and finish up the last few slides on Friday. Let me just